Okay, you've learned to do integrals in rectangular regions, and those are all pretty straightforward. What we need to look at is non-rectangular regions. Now, your book starts off talking about type 1 and type 2 regions and stuff like that. I'm just going to start off talking about common sense. Okay? And then you can read your book and see what type 1 and type 2 regions. I'll probably mention it as we go through. But it just comes down to common sense. So what I want to do is, first of all, okay, region. Y equals x squared and y equals 9 minus x squared. We want to do a double integral over this region of whatever function you like. Okay. And if you have that function, integrating with respect to x and y, you can do these limits. Okay. If it was a rectangular region. In other words, if x went from 0 to 5 and y went from 0 to 3, you'd have this rectangle, you'd go 0 to 5 dx, 0 to 3 dy, or in the reverse order, it wouldn't make any difference. Here, it's going to make a difference. Okay. I can describe the region. In terms of inequalities. It's x squared less or equal to y less or equal to 9 minus x squared. Okay. And 0 less or equal to x less than or equal to, well, we got to figure out what is less than or equal to. Okay. Right there is what it's less than or equal to, right? Well, 9 minus x squared equals x squared implies that 2x squared equals 9, x equals square root of 9 halves, which equals 3 times the square root of 2 over 2. So that's what I'm going to write. Understand what I just did? I just set this, the y value on this curve equals the y value on this curve. And that gave me the x value, which is times the square root of 2 over 2. Okay. I got two functions. Want to see where the graphs meet? I set the two functions equal, find the x coordinate. Then I can find the y coordinate if I need to. Turns out the y coordinate isn't going to matter, but it's going to be the square of this, okay, which is 9 halves, which means it's symmetric because, you know, right here, the y-intercept is 9. 9 halves is here, so you have a symmetry here, and you can, for a lot of reasons, think, why is this symmetric? Now, they won't always be symmetric. That's just a unique property that we want to be able to think about the functions in that context, but you learn. Okay, so. Okay. So now I can describe the region. So I've got a lot of X values. Let's take a bunch of representative X values, right? Let this be a typical X. I'm going to call it X star or X asterisk. On the line X equals X asterisk, here's the line X equals X asterisk. Here's Y is in the region R if lies between X star squared and 9 minus X star squared. Okay. So if I draw the point here, the point here, this much of the line is in the region. Does that make sense? I just that for a minute. So if I take an interval of the x-axis around this X star, okay, a small interval around this X star, then part of the region R that corresponds to this interval is approximately a rectangle. Okay. Now it's actually curving down a little bit up here, curving up a little bit here. It's approximately a rectangle. Now, if I do that for every I can take a sample point within the interval. I can sketch the X, the limits. I know what part of this line is within the region. And I can shade that. And I can be similar. So I'm going to get something that kind of looks like each of these is a little rectangle. It's a little increment of the area. Okay. I can imagine then what's here, little increment at a time, calculating, specifying the areas of the area. Okay. For the regions within those. Within each of these increments, I could specify I star. So that within this X increment, I have a Y increment. And within the X increment, I have a Y increment that's a square. Make sense? Okay, so this picture's getting a little fuzzy. So let's just say I've got some X increment. Some Y increment. This is a small interval for the X axis, small interval for the Y axis. Those intervals meet in a little square. Within this increment, or within this increment, okay. So now what I've got if I evaluate this at X star, Y star, I know about what the value of this is on this squaring. So I can multiply this by the area of that in. Okay. And that gives me the integral of this function for that in. Okay. If I divide the whole region up, it's not a very good picture of it. I divide the region up, I chop it up into X increments and Y increments. I can evaluate this function at some sample point within the increment and add up all those results, value of the function times the area. And that's going to give me an approximation of my interval. Now I'm going to cut to the chase here, and then I'm going to go back and blend the rigorous details. It turns out the limits on my interval 0 to 3 square root of 2 over 2 in this case, with respect to x, and from x squared to 9 minus x squared with respect to y. So we understand I'm letting x go from 0 to square root of 3 over 2. And then for every x, letting y go from x squared to 9 minus x squared defines this region. Okay. So without going into too much detail, this is how we get that integral. And that integral is going to represent what I did here is going to represent an approximation of the unit. I chop this thing up into x intervals and y intervals, and with each one, we multiply. I take a sample point, evaluate that function, multiply it, then by the area of the interval, and add them all up. That's going to be my interval. Okay. That's what this is going to represent. It's going to represent the limit of that process as the number of intervals approaches infinity, or more properly, as the length in which width of every interval uniformly approaches zero. Okay, limiting that. So to actually now evaluate this is fairly easy. I just do what we did for a rectangular region. With respect to y, I find an antiderivative, and I get well, my antiderivative with respect to y is going to be y squared over 2 here, so I have the x squared, y squared over 2. Then the antiderivative of y squared we use going to be y cubed over 3. Fancier than they do when you just have numbers here, because the integrals you did for homework, you just had numbers here. Now we've got expressions involving x. So what I have to do is I have to say, okay, this is x squared. X squared, y squared over 2, if the upper limit is x squared times 9 minus x squared over 2. Then I substitute y here to get x times 9 minus x squared cubed over 3. I forgot to put my square on this one. Okay. But we agree if with 9 minus x squared in here for y, both of these, this is what I get. And then I'm kind of out of room, so I'm going to do minus. Okay. Substituting x squared for y. Then xy squared becomes x times x squared squared. And this one over 3. Okay, so again, all I've done is I've substituted 9 minus x squared for y. That gives me my upper limit. Substitute the x squared for y, and that gives me my lower limit. Then I expand all this. And we just expand this, and we're just gonna get a polynomial in X that we can integrate from 0 to 3 squared root of 2 over 2. The point I want to make is okay, the big deal here is that this integral has to give me a function of X. Okay. And it gives me a function of X as long as my limits are functions of X. So my Y limits being function of X guarantees that. Okay. So I talked a little bit about what the integral means. You're just adding up the values of this function multiplied by little areas. And we get a lot more rigorous about that. Partition the intervals, form Riemann sums and stuff. We will. Let's get a handle on this first. Okay. Now, what if I wanted to integrate over function for the next parts to the orbits? And let's use this be y equals got the line y equals 3 here. Okay. Now, how am I going to describe that region? Here's the region enclosed by these curves. If I try to describe this region in terms of the X values, well, you see that from here to here, the X values go from 0 up to X squared, right? So for X from 0 to square root of 3, it turns out, I'd integrate from 0 to X squared. Then between here and here, I'd integrate, well, here I've just got a rectangular region, right? So y would just go from 0 to 3 as X goes from 3 to 4. This graph isn't to scale. And then from X equals 4 to X equals 7, as it turns out, I'd have to integrate from y equals X minus 4 up to y equals 3. We're not going to do that. That would be pretty messy, although it's certainly feasible, as long as you can identify what these points are and so forth. But I don't want to integrate with vertical cross sections. What I want to do is I want to integrate I'll say this, the easiest description of the region is zero less than y less than 0 less than or equal to y less than or equal to 3, and X squared less than or equal to X less than or equal to x minus 4. Sorry. Not filtering things at all today. I don't know what's going that was my brain. Okay. What are the inequalities that describe x? Here's a typical y. I'll have a y star. That's a typical y. Is x equal here? And what's x equal here? What's the value of x in this line if the y coordinate is y star? Think about it now. On the line, y equals y star, we encounter the graph of y equals x squared at this point. So if we know y, star, then on the y equals x squared curve, star equals x squared, so that x root of y star. I wrote that pretty small. But we're just saying, y coordinate is y star and y equals x squared. So y star equals x squared at this point. So we solve for x and you get the square root of y star. So this region starts when we hit x equals the square root of y star. Okay. And it ends at this point where star equals x minus 4, so x equals 4 plus y star. Okay. Now you understand that's a whole lot easier. You got to turn these functions around. You basically have to solve for x in terms of y in each case. Okay. So you have now y as a function of x. Another way to say it, y equals x star, x squared in the first quadrant at least, for x greater than 0, means that x equals the square root of y. So now x is a function of y. Here, we take y equals x minus 4. So x equals y plus 4. Just turn this function around, its inverse function. And you can immediately read things off with horizontal cross sections. Now that's what the book is talking about when they start out by saying, okay, you got type 1 and type 2 regions. They give you a mathematically rigorous definition of a type 1 region, which just means it's a region you can describe, region between two functions. Okay. That you can describe a vertical cross. Okay. And here use horizontal cross sections. They're more convenient. You could do this with vertical cross section. You would have to have three integrals. An integral from here to here, and an integral from here to here, and an integral from here to here. Okay. An integral by this, and it's not difficult. You just have to be able to turn around these functions and understand the logic of what I've said. Could have said it more clearly, but that's what's going on. So now if we want to integrate some function over this region, say we want to integrate e to the x plus 2y over this region. Then we get the integral. Y goes from 0 to 3. Or numerical limit first. And indicate, of course, that's the limits on the value of y. And then we integrate from square root of y plus y. And we integrate our function. This is with respect to x. So if the integral of e to the x plus 2y with respect to x is just e to the x plus 2y. And we evaluate that between square root of y and 4 plus y. And having done that, get a function of y integrate with respect to y. That's going to be e to the 4 plus 3y, which is easy enough to integrate, minus e to the 2y plus the square root of y. And you're going to have trouble integrating that. This e to the square root of y is not easy to integrate. Okay. Off the top of my head, I'm not even sure it's possible. I thought of it. Play around with some possibilities. There's no good integration by parts, maybe. Play around with integration by parts, just try substitution, I think it's going to work. And then you probably go to power series expansion and approximate it. Okay. Yeah, just do the Taylor series and do the square root. Well, that's easy to write down. You can do it out to any number of terms. So you get a good approximation. Okay, so whether you can integrate this or not, that's the way it works, right? So you got a type 1 region, a type 2 region, just common sense. You got a region, ask yourself whether you want to describe this in terms of cross sections this way or cross sections this. You want to break it up with respect to y or with respect to x. Okay. Now, the meaning is integral. Go back to our blocks. And we can understand tangent planes by understanding partial derivatives in terms of these blocks. Go back to what we did, the measurements we took. Okay, but we also understand volumes. Okay, so if this base is, again, let's have a better picture. What we're doing, we're going to integrate over region. Thinking of a typical x increment. Call this increment delta x sub I. Okay, it's like we've got an x sub 0 here, x sub n here. The delta x sub I, well, what I mean by the delta xi interval, we chop this up into a bunch of vertical strips. So that's clearly we can do this. So this interval is our delta xi. Take a sample point within that interval, and I'm looking for the right color of chalk, and I'm not finding it. This blue dotted line is on x equals x sub I star. Then we the line just try to decide the order by subscripts. Y equals y0 I. That's the lowest y value on the within the region within this strip. Okay. And I've I've used the I subscript, and I think I'm going to do y I0. And then up here, I do y equals y I m, and I put a subscript in there, m sub I. This is the highest y value within this strip here, within the region. Okay, so within the I strip here, take my lowest and highest y values, and then between those two values, to y sub j, and call that y sub ij. And a y sub ij star. So now I got this square increment here. Square increment, I can enlarge it. Goes between the line y equals yi j minus 1 and y equals ij. Okay. And j goes from 0 up to m sub I. Got x equals x sub I minus 1 here. X equals x sub I here. Got the line x sub I star in the line y equals y sub I j star. This means the increment on the ith interval of my x-axis. Okay. The jth y interval of that strip. So really all I'm looking at in this picture at this point is this green bonded region. And I've got this orange interval here. Now, if the function I'm integrating is e to the x plus 2y, my function, whatever function at this point, don't want to do too many labels. Clearly, this is the point xi star yij star. I'd like to have a little more room to write this out. The ij contribution integral over the region of f of x y is geez, I'm not on xi star Yij star. Now evaluate the function at this point. Times delta xi, that's delta yij. Can you read that? Why is it this? It's because that's the value of this function on this interval. That's the value of the function at this random sample point. And delta xi is the width, delta yj is the height or whatever. These are the dimensions. So this is the area. Okay, so this corresponds to this contribution of this increment to the f of x, y, dA. If we were to graph this function in 3 dimensions, it wouldn't be a quadratic surface. It'd be an exponential that would kind of go off like this, okay, in the first octave. And this block might represent this ij interval. It's ij rectangle here. That'd be the bottom of the block, sitting like this. And the height would be the value of the function at the sample point. So what you get is the volume. So this would be the volume over this of the function, whatever it is. If it's that exponential function, it's going something like this, be the volume of that function above this region. Okay. Now you can think of specific regions that we looked at before. Okay. But I'm just drawing a general region here. So that this integral could represent the volume of the function e to the x plus the volume beneath the graph of e to the x plus 2y above the region of the flow. Does that halfway make sense? It's one interpretation of a double integral of a function. It's a volume, and I think you saw that somewhat in the 5.1. Okay. Do they talk about density? Kind of think they might have, but again, maybe they saved that for this section. It's all kind of blurred together. I should have thought about that. Should have thought to look, but this could be the density. Okay, you've got a sheet of material here of varying density, where f of xy is the number of grams per cubic centimeter or whatever. So when you integrate the density over a region, well, it comes down to what you're doing on each end. If f of xy is the density function, f of xy is the density function, then you're multiplying density by area, which gives you mass. Okay. Or if it's density of electric charge, you'd be multiplying the density of electric charge times the area, assuming it's an area density, number of coulombs per square centimeter or whatever. You multiply the density by the area and you get whatever you have a density, a mass density, a probability density. Okay, probability density is important, and they are mentioned in one of the 3 sections. You're going to see them. Okay. Whatever kind of density this is, you multiply it by the area and you get the thing you're looking for. Maybe it's a probability, maybe it's a mass, maybe it's a charge. Okay. So that whole density idea is one you want to start pondering and thinking a little bit about. We'll talk more about it. Okay. Now, I'm going to talk briefly, and I want you to get started on the section on polar coordinates, at least a little bit. We have short time between now and the next semester. We got to do a lot of this over the weekend. That you see in rectangular coordinates, we split things up into little rectangles. Polar coordinates, oh, this is going to be good. I'm going to draw circles after drawing my axis. My axis, and it's getting worse. Okay, there's something representing some concentric circles, okay? Each of these, you have a constant R. Then you have lines of constant theta. Let's just say that this circle here is circle R equals R sub I minus 1. Now you can imagine there are a bunch more circles that are, closer than these are, hundreds of them or whatever. But right now we're just going to represent typically. Okay, so here we have an I minus 1, here we have an R sub I. In this case, this would be R1, R2, R3, R4, so that might be R2 and R3. And delta R sub I is R sub I minus R sub I minus 1. So here's your delta R sub I. Distance between these two circles. Okay. Over here, let's say that this line represents theta sub I minus 1. Right, the theta equals theta sub I minus 1, and this is theta equals theta sub I. And delta theta is theta sub I minus theta sub I minus 1. And your delta theta is just the angle between these two lines here. I'm not going to attempt to label it. Then where's the region between R sub I and R sub I minus 1? And between, I have to be careful with my notation. Label these. This will be theta equals theta sub I j minus 1. Delta theta sub j minus 1. Theta sub j. And delta theta sub j is theta sub j minus theta sub j minus 1. Okay, now, my region delta R sub I and delta theta sub J. Well, that's going to be this region right here. The dimensions of this region, this side and this side, are both delta R sub I. The difference in the R's. The width of this region depends on how far out you are. Further out, bigger the region. Okay? So I'm going to wave my hands a little bit. Say it's R sub I by R star delta theta sub J. Now I haven't defined R star. I'm going to do that in a second. Okay, here is the arc of the circle. Equals R star. For R star is just some radius between R sub I minus 1 and R sub I. Now, well, here is going to be delta theta sub J. R sub I minus 1. Is R sub I. Here's R equals R sub I star. I should have an I on it. By the definition of a radian, the arc distance here is equal to R sub I times delta theta sub J. If your delta thetas are small, in other words, if these radial lines are close together, this is almost a straight line, and this can be taken as the width of this region. So the area which I'll designate by delta Aij, the area between the I minus one and I minus one and RI circles in between theta j minus one and theta j is approximately then equal to, because this is approximately a rectangle, this delta RI. So I'm going to write it this way, RI star delta RI and the theta space. This leads to the area increment is RD theta. Integral interval might look like this. You have some function alpha bar theta, some function alpha that maybe gives you the height above this region of a plane so that this integral would represent an area. Okay. Limits in your inner integral for integral is the r dr. Have some function of theta here. And then it have limits on theta out here. And we don't have time to get into details of that. But I want you to focus on what I'm saying here, that the just as wherever it went, your interval in XY coordinates, your natural interval is a rectangle, a delta X by delta Y rectangle. In polar coordinates, you have this kind of flared out region. It has dimensions of delta R. And if it's a small enough region, then it's going to have an area very much like that of a rectangle described here. We want to understand this. That's just the definition of a radian. Arc distance is equal to the angle in radians times the radius of the arc. Okay. And that's the definition of a radian, which you want to keep in mind in yourself. Some people tend to lose track of it. And also, you know, I had a really pretty good high school preparation with the exception of a theoretical math course instead of recalculus. So I had to figure out a lot of stuff. But then I had a lot of stuff behind me that, you know, I didn't really understand writing. It took a while to make that notion intuitive. So I kind of want to remind yourself that it's an important picture. And we'll go on with it next time and see how to do integrals in polar coordinates, which are not particularly difficult, as long as you remember that RD theta thing. Okay. And then we'll do some volume integrals. So try to get the section 5.2 done pretty well and take a look at section 5.3. Maybe do a couple of problems there.